Hello, everybody. Welcome to SysGuide's YouTube channel. In this video, I will show you how to secure the pre-boot environment of your Fedora distribution by enabling UEFI Secure Boot with your own custom keys. I'll show you how to generate your own UEFI Secure Boot custom keys and how to self-sign all of your bootloaders, kernels, and kernel modules with your private key in order to safely boot the operating system. Secure Boot is based on the idea that UEFI firmware should only pass control to the operating system if it can cryptographically validate boot components against a pre-distributed set of public keys and hashes. When you turn on the computer, the firmware verifies each boot component's signature or computed SHA-256 hash. If the signatures or hashes of all of the boot components are valid, the computer will be allowed to complete its boot process, and the firmware will hand over control to the operating system. To keep this video simple and secure, I installed a fresh copy of Fedora 39 Workstation under KVM virtualization with Secure Boot enabled. I'll use this virtual machine to demonstrate all of the steps I'll take, such as key creation and enrollment, signing various binaries, and so on. I strongly recommend that you do the same before enrolling your custom keys on your actual computer. Experiment with all of the commands first on the virtual machine, then apply them to your actual computer if you're happy with the results. I also have a text version of this video where I go over how to secure the pre-boot environment in greater detail. Please take a look at the web page as well. I'll include a link to the web page in the description. So let's get started. Before you can begin configuring or reviewing UEFI Secure Boot, you must first install a few packages. So install these packages. The top level key used in Secure Boot is PK, the platform key. PK establishes a trusting relationship between the platform owner and the platform firmware. In a system, UEFI Secure Boot only supports a single PK. If a PK already exists, you cannot add another unless the existing one is removed. The PK holder can update or replace the KEK, key exchange key, as well as replace an existing PK. The PK is typically owned by the OEM, who has complete control over the Secure Boot keychain. So if you want complete control over the Secure Boot process, you must replace the PK with your own. So find out who is currently in possession of the PK. As you can see, Red Hat owns the PK because KVM is a Red Hat Inc. product. If you check it on your actual computer, it is usually owned by the OEM. To view the public key in the PK, use the command mock-util --pk. As you can see, there is only one key. The signature algorithm is SHA-256 with RSA encryption, which is the recommended algorithm. The certificate is issued by Red Hat. The certificate is valid until October 25th, 2037, or roughly 23 years after it was issued. And the public key is encoded with RSA encryption and has a length of 2048 bits. In this tutorial, you will be replacing Red Hat's PK with your own PK. The next key in the secure boot key hierarchy is the KEK, or key exchange key. KEK create a relationship of trust between the platform, firmware, and the operating system. KEK are used to sign signature database and forbidden signature database. On most systems, there will be one or more KEKs. KEKs are used by vendors who need to update the signature database or forbidden signature database. Vendors include OEMs like Acer, Bell, and others, as well as operating system providers like Microsoft and Red Hat. So let's take a look at the KEKs that have been enrolled. As you can see, 2 KEKs have been enrolled. One is provided by the hardware manufacturer, in this case Red Hat, and the other by Microsoft Corporation. Both KEK owners will be able to update the signature database and the forbidden signature database. To view public keys in the KEK, run the command mock util --KEK. You can see 2 public certificates from Red Hat and Microsoft Corporation. The signature algorithms used for both certificates are SHA-256 with RSA encryption and public key algorithm with RSA encryption, each with a 2048-bit length. In this tutorial, you'll delete both of these keys in KEK and replace them with your own. The next key is DB, or signature database. DB is essentially a boot binaries whitelist. DB contains public keys of the signers or image hashes of boot binaries. Boot binaries with signatures that can be validated by a public key in the DB will be allowed to execute at boot. Similarly, binaries without a signature, but with a computed SHA-256 hash that matches a trusted hash in the DB will also be allowed to execute at boot. Examples of binaries include boot managers, bootloaders, kernels, and kernel modules. So let's take a look at the DBs that have been installed. As you can see, you have 2 DBs installed. Both were pre-installed by Microsoft. The first DB is used to validate the Microsoft Windows operating system. And the second DB is used to validate Microsoft Corporation approved third-party vendors. To view the public keys and hashes that have been added to the DB, run the command mockutil --db. As you can see, you have 2 public keys enrolled. Both are from Microsoft. You will delete both of these DB keys and replace them with your own. This method has both advantages and disadvantages. The advantage include complete control over which binaries can be loaded. The kernel and most of the kernel modules will already be signed with Fedora's built-in Fedora kernel signing key. Other than that, each binary must be signed with your own private key. As a result, your secure boot is completely secure. Nothing can sneak up on you unless you give it permission to. The disadvantage is that you must sign everything that will be loaded during the booting process. Although there will be few, if you are not technically savvy, it may be inconvenient. Furthermore, the majority of vendors are Microsoft certified. And if the software or hardware of such a vendor is involved in the boot process and you do not have their keys installed, the system will not boot. In order for it to boot again, you must sign each of them with your own private key. I suggest you start with your own keys and self-sign anything that prevents the secure boot process. If you dual boot with Microsoft Windows, you can even use your private key to sign the Microsoft Windows bootloader. You will have no problem. And if you think it's too much, you can always restore Microsoft keys. Check out my article on the same subject where I explain how to do so. I'll include a link to the webpage in the description. The last key is BDX, or Forbidden Signature Database. The DBX is a kind of anti-DB. DBX contains public keys of the signers or image hashes of boot binaries. DBX is used to validate the undesired binary that you do not want the system to execute when it boots. If a binary matches a key or hash in both the DB and the DBX takes precedence and the binary is not allowed to execute. So let's take a look at the public keys and hashes that have been added to the DBX. As you can see, there are a lot of hashes. There is a single DBX list with SHA-256 hashes. By comparing each SHA-256 hash of the binary to the one provided by Microsoft KEK, you can conclude that it was added by Microsoft. There are no public keys of any signers in this DBX, only SHA-256 hashes of binaries. In this video tutorial, I will remove this DBX. You won't need the DBX because you'll be creating your own DB with your own custom key enrolled in it. If you don't want a binary to execute at boot, don't add it to the DB list in the first place. This is not the case with vendors such as Microsoft or Red Hat, who will have already signed a large number of binaries with the same private key, only to discover later that some of them have been compromised or are out of date. As a result, such binaries are added to the DBX blacklist. To enable secure boot, you must have PK, KEK, and DB. DBX is optional. However, if you want to add the most recent Microsoft list of prohibited hashes to DBX as well, please see my article on the same subject where I explain how to do so. Okay, this brings us to the end of our overview of UEFI Secure Boot keys. Before you begin generating your own keys and adding them to UEFI Secure Boot, I strongly advise you to make a backup of the original UEFI keys. You might need them later. So switch to the super user. Create some directories where you can back up not only UEFI Secure Boot keys, but also other types of keys. You can create directories wherever you want and name them whatever you want. Just make sure that only you have access to them. Now make a backup of the original keys. First, save the output of the EFI readvar command to a text file. After that, save the original platform key. Save also the original key, exchange key. save the original signature database. And finally, save the original forbidden signature database. The backup of your original UEFI Secure Boot keys is now complete. Now that you saved the original UEFI Secure Boot keys that came with the computer, you can safely remove them from the firmware. So boot into the firmware of your computer. Since there are different methods for removing keys in different firmwares, I will only show you how to do it in the KVM virtual machines firmware. On the firmware main screen, select the device manager, scroll down and select Secure Boot Configuration. Then select Reset Secure Boot Keys. Press Yes to confirm. Finally, reboot and return to your operating system. After rebooting, confirm that all entries in the secure boot chain have been removed. Now check the status of secure boot. As you can see, secure boot has been disabled and the platform is in setup mode, which means you need to provide a platform key. Now that you've removed all secure boot keys, I'll show you how to generate your own custom keys in the following section. With all of the UEFI secure boot keys removed from the firmware, you must now generate your own secure boot keys. Microsoft recommends that the keys be of the type EFI cert X509 GUID with the RSA public key algorithm, a public key length of 2048 bits or higher, and the SHA-256 RSA signature algorithm. I will generate keys with RSA 4096 bit strength, which is supported by the vast majority of modern computers. So create a new file called pk.cfg. And then go to my webpage on the same topic. This is the URL. And then copy the text. And paste it into the pk.cfg file you just created. As you can see, I have set the default key size to 4096 bits. If your computer cannot handle 4096 bits, generate keys with 2048 bits instead. I have set the common name to sysguides platform key. Change it to something relevant to you. The email address is optional. You can either set it or leave it. The flag CA false indicates that the certificate was self-signed rather than issued by a certificate authority. And if you want to know about the other options and extensions in the configuration file, refer to their man pages. Save the file and exit. Now, generate an X509 certificate key pair for platform key, the PK, using the pk.cfg configuration file. I'll set the validity period to 15 years, taking 366 days into account for 1 calendar leap year. The X509 certificate must be in PEM format. Press Enter to generate keys. As you can see, a pair of private and public keys for the PK have been generated. Now take a look at the PK public key. As you can see, the signature algorithm is SHA-256. With RSA encryption, the certificate is valid until October 13th, 2038, or roughly 15 years from the date of creation. The common name, in my case, is SysGuide's platform key, and the public key is 4096 bits. Now generate an X509 certificate key pair for the key exchange key. To do this, copy and save the previously created pk.cfg file as kek.cfg. Open the kek.cfg configuration file and replace platform key with key exchange key in the common name field. Save the file and exit. And using the kek.cfg file and replacing pk with kek in the previous command, generate an X509 certificate key pair for key exchange key. Take a look at the kek public key. The common name in the certificate is now, as you can see, is SysGuide's key exchange key. And finally, repeat the process for signature database as well. Copy pk.cfg as db.cfg. Open the db.cfg configuration file and replace platform key with signature database. Save the file and exit. Now generate an X509 certificate key pair for the signature database, the DB. Replace kek with db in the command. And press enter. Check the DB public key and confirm that the common name is SysGuide's signature database. List all of the generated keys. As can be seen, RSA 4096 bit private and public keys for PK, KEK, and DB have been generated. As I said earlier, you don't need a DBX key in order to enable Secure Boot You just need PK, KEK, and DB. DBX is optional. This brings us to the end of this section. In the following section, I'll show you how to convert the certificates you just created to AUTH format so that you can enroll them in UEFI firmware. While you created your private and public key pairs in the previous section, the public part of the keys are in PEM format. You cannot directly enroll PEM format public keys in Secure Boot's value store. Before certificates can be loaded into Secure Boot, they must first be converted to EFI signature list files, also known as ESL files. Some firmwares allow ESL files to enroll directly in Secure Boot's value store. However, if you want to enroll keys using the command line interface in Fedora, the keys must be in AUTH format. The AUTH file is simply an ESL file with an authentication header. So the first step is to convert your public keys from PEM to ESL format. Then sign ESL files with your private key to convert it to AUTH format. Also, for the keys to have the EFI CERT X509 GUID type signature, you must provide a unique ID in the 844412 format. This is recommended by Microsoft. So generate a unique ID. And then save it to a file called guid.txt. As you can see, a unique ID in the format 844412 has been generated and saved in the text file. This will be your owner's unique ID, which you will use in your custom keys. Now, using this GUID, first convert pk.pem file to pk.esl file. To do this, run the command cert to EFI siglist. Your GUID pk.pem as the source file and pk.esl as the target file. Next, create a pk.auth file. To create a pk.auth file, the pk.esl file needs to be signed with the pk public and private keys. For this, use the command sign EFI siglist -G, your GUID, -T, timestamp, -C, your pk.pen public key, -K, your private key, pk.key. The PK, or platform key, a top-level key used in Secure Boot. The source file, pk.esl. And the target file, pk.auth. Now, create a KEK auth file in the same way. First, create a kek.esl file from the kek.pem file. Replace pk with kek. Then create the kek.auth file. Replace pk with kek here as well. Please keep in mind that for kek, you must also sign with the pk public and private keys. Finally, create a db.esl file from the db.pem file. And create the db.auth file. For the DB, however, please note that you must sign using the kek public and private keys. Replace kek with DB and press enter. All of the pk, kek, and db auth files have been created. In the section that follows, I'll show you how to enroll these auth files in the Secure Boot value store, as well as sign your bootloader and kernel. Now that you've converted all of your public keys to auth format, you must enroll them in the Secure Boot value store. It is important to enroll auth keys in the correct order. You must first enroll db.auth key, then kek.auth key, and finally pk.auth key. So first enroll db.auth key into the db variable. The command is EFI update var -f, your db.auth key, and the variable you want to update, that is db. Next, enroll kek.auth key into the kek variable. And finally, enroll pk.auth key into the pk variable. All of your keys have now been enrolled in the Secure Boot value store. So check each of the variables to ensure that your custom keys are enrolled. First, check the primary key. As you can see, the PK now has your key. So you now have complete control over the Secure Boot keychain. Now look at the key exchange key. The KEK now has your key as well. With your key enrolled in KEK, you can now add, remove, and update X509 public keys or SHA-256 hashes in the signature database. And finally, check the signature database. The signature database, abbreviated as DB, also contains your key. When you sign your boot binaries, such as the bootloader, kernel, and kernel modules, UEFI Secure Boot validates the boot components by using the public keys and hashes stored in this signature database. And if they are valid, the computer will be allowed to complete its boot process, and the firmware will hand over control to the operating system. Also, take note of the owner GUID. It is the same for all variables such as PK, KEK, and DB. It is also the one you generated and saved in the file guid.txt. This will be your GUID, and whenever you see it, you'll know it's your key. All right, you have now finished enrolling your keys. But don't reboot your computer just yet. To complete the process, you must still sign your bootloader and kernel. When you sign the bootloader and kernel and reboot, Secure Boot compares the signatures in the bootloader and kernel to the X509 key in the DB, and if they match, you will be able to boot. So first, locate your bootloader. To find out which bootloader is currently active on your computer, use the command bootctl status. Look for the status that is active and the path to the bootloader. The bootloader in this case is shimx64.efi. Let's see who has already signed the shimx64 bootloader. As you can see, it is signed by Microsoft. If you recall, at the beginning of this video, you removed Microsoft from the DB. With no Microsoft key in the DB, if you try to boot with this bootloader, Secure Boot won't allow you to boot. You can either replace the Microsoft signature with your own or simply append your signature to it. I will, however, replace it with my own. Make a backup of the original bootloader. So first, remove the Microsoft signature. The PE sign tool does not yet support in-place writing. As a result, you must first output to a different file. I'll name the output file as shimx64.efi.empty. -u0 is the first signature number indexed from 0. Examine the shimx64.efi.empty file to ensure that the Microsoft signature has been removed. As you can see, the Microsoft signature is no longer present. Now use the SB sign tool to sign the shimx64.efi.empty file with your DB private and public keys, and replace the original shimx64.efi bootloader. You may receive a warning that reads something like this. I did some research, and it appears that these are harmless and can be safely ignored. Now check the shimx64.efi bootloader once more. It should now have your signature. Now that you've signed the bootloader, you can delete the shimx64.efi.empty file. As for the kernel, let's see who signed it. As you can see, Fedora has already pre-signed it. When a kernel or even kernel modules are loaded in Fedora, their signatures are validated using the X509 key from the built-in kernel system keyring. That is .builtin_trusted_keys. If any of the signatures is validated by a key in the built-in kernel system keyring, the kernel is allowed to load. If the signatures cannot be validated using the built-in kernel system keyring, then the third-party kernel platform keyring, that is .platform, is used. The platform keyring includes keys from third-party platform providers such as OEM, as well as your own custom DB public key. So let's see who has keys stored in the built-in kernel system keyring. As you can see, a Fedora kernel signing key already exists. So there is no need to sign the kernel because it is already signed by Fedora and not by any third party. If you enable Secure Boot right now and reboot, everything should work perfectly. However, I'm going to sign this kernel anyway, just to demonstrate how to sign a kernel if you use a custom kernel or dual boot with a kernel that hasn't been signed by Fedora. So the command is sbsign your kernel, your DB private, and public key, and the output the kernel itself, replacing the earlier one. Recheck the kernel for signatures. It now includes your signature. Now, reboot your system. After the reboot, confirm that Secure Boot is enabled on the system. As you can see, Secure Boot has been enabled and the platform is in user mode, indicating that Secure Boot is active. Also look at the kernel platform keyring. It contains keys from third-party platform providers, as well as your custom public keys. It should now include your signature database, that is DB key. All right, you now have a computer with a pre-boot environment secured with your own custom keys. This brings us to the end of this section. In the following section, I will show you how to sign the kernel modules. The kernel modules that come with Fedora, like the kernel, will already be signed by the Fedora kernel signing key. To see if the kernel module has already been signed, use the mod info command. For example, I'll use the kvm_intel kernel module to see if it's been signed. You can, however, use any other kernel module included with the Fedora Linux distribution. The command is mod info-f signer and the kernel module. As you can see, the kernel module has already been signed with the Fedora kernel signing key. And in this case, the built-in kernel system keyring is used to validate the signature. As an example, let me show you how to sign VirtualBox kernel modules. When you enable UEFI Secure Boot and try to run the VirtualBox guest virtual machine, you will receive this error message. According to the error description, you must sign these 4 kernel modules. So first, check if the VBox DRV kernel module is loaded. There is no output. This indicates that the VBox DRV kernel module is not loaded. Now verify whether the VirtualBox kernel modules have been installed. Except for VBox PCI, I have all other modules installed. My setup probably doesn't require it, but it could have been installed on yours. Go to the directory where VirtualBox kernel modules are installed. So sign all kernel modules with your DB keys. The syntax is sign file, SHA-256, your DB private key, your DB public key, and the kernel module. Verify that the module has been signed. The kernel module now contains your DB signature. Now sign the other two kernel modules as well and check for signatures. I'll quickly go through the process again and sign the other two VirtualBox kernel modules. After signing all of the modules, manually load the VirtualBox kernel modules. Verify that the VirtualBox kernel modules have been loaded properly. Now start the VirtualBox application again and check if you can run the guest virtual machine without any problems. Signing the NVIDIA kernel modules is similar to signing the VirtualBox kernel modules. Regrettably, I'm unable to show you how to sign the NVIDIA kernel modules as I am currently running the Fedora distribution in KVM virtualization. However, you can go to my website and read a text version of this video in which I explain in detail how to sign NVIDIA kernel drivers. The only difference between the two is that NVIDIA kernel modules are compressed. You must first uncompress them, sign the modules, and then compress them back. If you have an NVIDIA card installed on your system, I recommend that you visit the web page to learn how to sign the NVIDIA kernel modules. In the article, I have also explained how to enroll Microsoft keys if you wish to do so. Take a look at that as well. All right, this brings us to the end of the video. You have now finished securing your pre-boot environment by enabling Fedora UEFI Secure Boot with your custom keys. And thank you for sticking with me all the way to the end. Please subscribe to my YouTube channel so that you can be notified whenever I upload a new Linux video. Take care, and until next video, bye-bye.